Let's look at some qualitative predictions about entropy. Do y'all know what qualitative means? It means no numbers. Okay? It just means, is it getting more disordered? Or, yeah, it's just kind of yes or no. Keep it in mind that positive S means disorder, and negative S means more order. And we're going to look at table 18.2 on the bottom of page 782. The first two things listed on that table, I don't have one to pull up here and show you. So if you don't have a book, maybe look on with your neighbor. But it's H2O liquid and H2O gas. And the table actually gives you numbers for entropy. You can tell by the number that H2O gas has a higher entropy. It's more disordered. And you know why that is, because it's a gas. And we just said that gases are more disordered than liquids. You can compare the same thing when you look at the next three. You've got sodium, the entropy for sodium in three different phases: solid, liquid, gas. Gas is much more disordered than a liquid, much more than a solid, etc. Okay, now go to the helium and neon. Both of those are gases, and both of those are monoatomic. Neon has greater entropy. You can tell because you can look at a number on that table. But if you didn't have the number, how would you know that neon is more disordered than helium?
Because it's farther to the right.
Molar mass. What does a higher molar mass mean? Doesn't that mean, y'all, that it's got more protons and it's got more electrons? So doesn't it have more subatomic particles that can be moving around, and it's larger? Okay? So if you're comparing two things that are the same type, and in this case two monoatomic gases, you can look at molar mass. You would not, for example, want to compare water vapor and neon gas, because those aren't like each other. Okay? Yes. To you about is like methane and ethane. Y'all, methane is CH4. Ethane is C2H6. There's molar mass to consider, okay? Ethane's going to have a higher entropy. But sometimes you can also consider how they're bonded to each other. Because another criteria, if you will, that's used to determine entropy is the number of bonds and the freedom amongst those bonds. If you just look at these structures, the one on the right, the ethane, look at all those bonds, y'all. There's movement around those bonds. There's rotations of those bonds. There's some telescoping in that they're getting longer and smaller. Okay? And so all of that movement contributes to the entropy. Perhaps a better example would be to compare that one I have on the right. I'm about to erase, okay? Well, I thought I was. To this. Huh? Yeah. Do you see that in that one on the left, now there's even less freedom because of that double bond? Tied it up just a little bit more, and it's less disordered. The one on the right is still more disordered.
I actually have a quick question.
Keep on making some qualitative predictions on entropy, y'all.
So
And
because it's double bonded, it's less freedom.
it's less freedom, so it's more ordered.
So if you have
So the bond's
Well, here we go. Y'all got me off the subject. If we look at that table, I've given you some things to look at for is entropy increasing or decreasing. Now, let's look at a chemical reaction. Calcium carbonate solid. When you heat that, y'all, it'll decompose into solid calcium oxide and CO2 gas. Can you look at that balanced chemical equation and make a prediction as to a positive S or a negative S? Why positive S? Since it's producing a gas, I expect this S to be increasing. And that's what we're going to find, but that would be the prediction I'll make. Okay? I'm going to give you another one. Can I switch slides?
Not yet.
Negative.
That's tricky because we can't just look at the gas thing. That's what we could look at in the first one, but everything's a gas.
More moles on the left. Right?
Ah, yeah, why? Y'all are answering it. Because the left side's got 4 moles of a gas, and the right side has 2 moles of a gas. So it's becoming more ordered. Positive S or negative S? Positive. Negative, and I was recording that, so, oh well, sorry. Yeah, it's becoming more ordered. I'm sorry.
Do you have to
Y'all
put the
answered it right, and then I changed your answer. What's that?
Do you have to put the delta, or can you just put negative?
You don't have to have the delta.
So what if they're
What do you do here? There-
Use the bottle of bass, don't
No, you don't know. That's the answer. You cannot predict this one. You got 2 moles on the left, 2 moles on the right. It's gases on the left, it's gases on the right. You can't use molar mass because HCl is a very different compound than chlorine or than hydrogen. So you can't look at molar mass. So you can't predict this. You don't know. You would have to calculate it. How would you calculate it? Y'all are doing so great with your questions.
Leading right to it.
Do you remember a formula that looked... Hang on, I don't want to mess it up. No, y'all can't ask any more questions. Delta S of a reaction is equal to the sum
of the moles of the product?
of these of the products.
So
Remember this? Something like it from Chem 1?
yeah, but it was for
Enthalpy.
yeah.
It was for enthalpy, but we use this in Chem 1. There's an appendix in the back of your book. It's called thermodynamic data. And you use this in Chem 1 to look up enthalpy, but there's other numbers in that table as well. There's entropies, and then there's a G, which we're going to get to eventually. But we go to that appendix, and we're going to use this formula to calculate what the delta S is for this equation we have written. I'm going to erase the formula, and I'm going to show you how to use it. It's Appendix 2. It starts on A7. So you go to Appendix 2, you find calcium carbonate solid, and you look up the entropy, the standard entropy for calcium carbonate. That's the gas, yeah. Okay, so those numbers we get from our appendix. We look them up in the back of the book. Then you have to multiply each one by the coefficient. That's what the N and the M were in that formula, but it just so happens on this one that, yeah, everything gets multiplied by 1. If it had a coefficient, that's where you would multiply it. What did those little funny things like this, the sigmas, what does that mean? Sum of. So you take the sum of the products.
I have a question.
Yeah.
Where'd you get the calcium oxide?
The table, CaO. I think it was a little bit above calcium carbonate, wasn't it? Okay. And that will give you the standard entropy change for this reaction. It's positive what?
160.5.
Positive 160.5 joules per Kelvin mole. We had predicted that it would be positive earlier, remember? I still have that written up here, that's what we predicted, and indeed we get a positive 160.5.
We add the products together and multiply them.
You sum up the products
And we
and the reactants and then subtract products from reactants.